right. So if at any point you guys have questions, just let me know. I will address anything. Especially if you want to start off with SN1, SN2 confusions from last week, I can go ahead and start off with that. If not, I will get into E1, E2. Okay. And when is y'all's exam? Should be October 28th or 21st. 28th, okay, yeah. All right, so you guys got a little bit of time because you guys have a quiz over elimination this Thursday, actually. That gives you guys about a week and a half until the exam. All right, so I don't see any questions regarding SN1, SN2, so hopefully you guys are good with that. I know it gets a little bit tricky, but hopefully you guys have enough practice that you guys are able to distinguish between those two. Now, E1, E2, before we get into that, let me quickly tell you guys the differences. Okay, so let me do one, SN2 here, and E1, E2 here. Okay. So basically, SN1, SN2 deals with, first of all, deals with substitution. That's what the S stands for. And you are substituting the nucleophile with the leaving group, okay? So the nucleophile is replacing the leaving group, and it does this by attacking with the negative charge and finding a positive charge on your electrophile, okay? And then, like I said, you are dealing with nucleophiles, so that's another kind of difference. And yeah, that's honestly, that's pretty much it. For elimination, of course, to start off, you are not substituting anything. You're not substituting your reagent. You are using that reagent to eliminate your leaving group. Okay. Well, your leaving group is already leaving anyways, but you are also eliminating an additional hydrogen. So instead of providing electrons to the carbocation, instead you are relieving of that carbocation or lack of electrons by getting rid of a hydrogen and placing a double bond to satisfy both carbons. And then, of course, by abstracting a hydrogen, you need a base instead of a nucleophile. Okay? Bases will help you abstract that hydrogen. Okay. All right. So that's kind of just a very general differences. Okay. And then just to slightly add on, just so you guys can remember, you will always create a double bond for E1, E2, okay? So if you think it's elimination, but you somehow don't end up with a double bond, that means you probably did something wrong in your answer choice. Okay? All right. So now to actually go over the differences between E1 and E2, I will create a flowchart, or not a flowchart, like a table, exactly what I did last week with SN1, SN2. So E1 is going to be in red, and E2 is going to be in blue. And please, at any point, just stop me if I am saying anything that doesn't make sense or you guys haven't covered yet or you want me to elaborate. All right, and then I will put like the tools in black. Okay. All right, so first off, we talked about bases. In SN1, SN2, under our tools, we had nucleophile, right? So now instead of nucleophiles, we're going to have bases. And specifically, we're going to look at two things. We're going to look at strength of the base as well as size of the base. And I'm going to put the size of the base a little down below. Okay. All right, and there is also a unique special thing with each of them. And I'll just say special. Right? Okay, so can anyone tell me what the strength of the base for a E1 mechanism is? Is it a weak base or a strong base? That's correct. It's similar to its SN1 component. It is a weak base. And of course, if that's weak, that means E2 has to be a strong base. Okay? It's very straightforward. Right. And that's for its strength of the base. So just like a strong and weak nucleophile, you have the same thing, except it's a strong and weak base. All right. Now the special point of contention is that E1 can do something very similar to SN1. Does anyone know what that is? Starts with the R. Resonance is a good guess, but it's actually rearrangement. So just like SN1, E1 can also do the methyl and hydride shift. But only E1 and SN1 can do this. E2, SN2 cannot rearrange. All right. And does anyone know what the special thing for E2 is? Oh, sorry, this is supposed to be in red. I'll just rewrite it. Chirality flip. Okay, I think you're on the right line. We're on the right track. Let me just quickly do this. Rearrangement. Right, so that's very close, but we call it, or the proper term is called anticoplanar hydrogen. Okay? And what this means is that when you are eliminating both your leaving group and hydrogen, it has to be anticoplanar. Okay, anticoplanar means it is on opposite planes. Okay, and to put it in other terms, it is going to be trans from each other. Okay, so to give you a visual aspect, your leaving group, let's say it's on a wedge, and I will denote it as Lg. Your hydrogen must be on a dash for you to get the go-ahead to eliminate both of these and then place a double bond right here. If your leaving group is on a wedge and your hydrogen is also on a wedge, you cannot eliminate both of them because they're on the same plane. Okay, so you would then have to rotate this carbon so that the hydrogen is now on a dash instead of the wedge. Okay. But because everything's multiple choice, you might not have to do that, or well, you guys will have to see your answer choices and decide for yourself. But just like that, your leaving group can also be on a dash. Okay. If it's on a dash, that means, of course, your hydrogen has to be on a wedge. Okay. And if you notice, they have to be directly adjacent. Okay, only one carbon away. All right, so in some situations, they will specify the chirality or stereochemistry of your hydrogen. In other cases, they will not, and you will get the option of both a wedge and a hydrogen, specifically in a ring. And I will show you guys what I mean. Okay, but any questions so far before we get to size? For the special on E1 side, the words overlap. I'm not sure what you mean. I don't see overlap for me. I mean, I guess I can try. Oh, really? What about anyone else? Okay, maybe I'll just put it underneath. Because, okay. I'm sorry about that. Maybe I'll just scoot everything down. That's weird. I erased on my screen. Okay. Yeah, but all I'm trying to say is that it can also rearrange just like SN1. And it can do that with a hydride or a methyl shift. Okay. Now, on to the size of our base. You could have a small base, or you could have a not big, but we call it bulky. Okay. Now, size of the base does not determine E1 or E2. E1 and E2 is only determined by the strength and, or actually just the strength of the base. Okay, so if it's a weak base, it's automatically E1. If it's a strong base, it's automatically E2, regardless of the size of that weak base or the size of that strong base. Okay, what small and bulky bases denote, and let me actually put that in a different color. Okay, if I erase small, do you guys see that? Or the small disappeared, right? Okay, good. Let me get rid of bulky also, and let me put it in two different colors. Okay, I'm going to put small in green and bulky in orange. Okay, are we good, or is it overlapping again? Okay. All right, so so if you have a small base, you are going to place your double bond on your double bond is going to be it's going to have more substituents, okay? And I will just simply write more sub, okay? If you have a bulky base, your double bond is going to have less sub. Sub means substituents, okay? Um, okay, and then so now I will actually show you what I mean, okay? So I'm going to use, oh, sorry. I'm going to use a generic example to show both of these. Excuse the drawing. Okay. So let's say there is a bromine at this tertiary carbon. Okay. Now that bromine is in between 3 different carbons. Okay. And these 3 different carbons all have hydrogens. Okay. So let me draw in our hydrogens. So we have 3 right there, 2 right there, 2 right there. Okay. And let me actually write out each of those. Okay, notice I didn't put any wedges or dashes. That's because, well, because we have 2 hydrogens, we have to assume that there is 1 wedge and 1 dash for both of these. And then, of course, when you read, you have 2 of one and 1 of the other. Okay. All right. So, this is our leaving group. Okay. And that leaving group is in a tertiary position. Okay. Which doesn't really matter in this case. So in order for you, so you can either create a double bond between a bromine and a hydrogen, okay? So that means it could be right here, it could be right here, or it could be right there, right? You have 3 different options, okay? If you go either up, or sorry, if you go either left or down, you get the exact same thing, okay? So I'm only going to consider the bottom one and the top one, okay? Because this one, this side, and this side are the exact same, okay? So you can either, and to go down, you would actually get your more substituents, and to go to the right, you would get your less substituents, okay? So to redraw this, let me redraw the structure. The reason why I am placing my double bond here is because if I do this, I have I have 1, 2, 3 substituents on my double bond. Okay, so this has 3 substituents on this double bond. Okay, does everyone see that? Okay, and then I'll redraw it for my bulky base. Draw my double bond, and then find my substituents, which are these 2 carbons. These 2 carbons are directly bonded to my double bond, and only these 2 carbons. These 3 carbons are directly bonded to my double bond, and only these 3 carbons. This carbon is not bonded to this one. These 2 carbons are not bonded to this one. Okay, are we all on the same page now? All right, perfect. Okay, now to explain a little bit of the conceptual side of things, so you guys are not simply memorizing this, let's imagine you are a small base, okay? If you are a small base, you have more freedom to grab these more sterically hindered hydrogens, okay? Secondary hydrogens are more sterically hindered than primary hydrogens, okay? Because primary hydrogens are in the open, they're sticking out. These are slightly more sterically hindered, okay? If you are a small base, you have no trouble reaching those sterically hindered hydrogens, okay? You can quickly go in, abstract an H, and get out, okay? However, if you are a more bulky base, you have a large electron cloud, you are going to have a slightly more difficult opportunities to obtain those same hydrogens that are sterically hindered. Okay, that's why you have to go for more accessible, less sterically hindered hydrogens, which are primary hydrogens. Okay, that's why when we have a bulky base, we always create this product, which is on the outside. And small base, we create this product, which is on more inside. Okay, more substituted. Okay, and the terminology for small base is called Zaitsev. Okay, Z-A-T, Zaitsev. I think I spelled that correctly. And then for a bulky base, this product is called a Hoffman elimination. Okay, so Zaitsev elimination and Hoffman elimination. So let me move everything so it's in the center. Okay. So those are the names of these specific products, and once again, these do not. This Zaitsev does not mean E1, or Zaitsev does not mean E2, and likewise, Hoffman does not mean E1. Hoffman does not mean E2, and these are completely separate from E1, E2. Okay. So some examples of small bases or typical bases that you will encounter are, maybe I'll just put it in, yeah, I'll put it in green. So we know it's Zaitsev because this double bond has more substituents, okay? And we are also using a small base, okay? If we are using a bulky base, okay, all right. All right, so to give you examples of small bases, the most typical common one is NOOH, as well as H2SO4. Okay. These should tell you right away that you are creating a Zaitsev product. We'll just put it right next to each other. Okay. Now for bulky base, if you see LDA, that's one. And then another one is called terbutoxide, so T-butoxide. And terbutoxide is also it usually looks like this with the terbutyl, and you have a O minus. Okay, and the reason why you have a O minus is because this is usually paired a potassium or sodium, K or Na. Okay, so if you see this structure, or terbutoxide, which is the same thing, or LDA, you're dealing with bulky bases. Okay, usually bulky bases are more, or there's very few of them. From what I've experienced with, these are the main two that you guys should deal with. Hardly ever they introduce another bulky base, but So this is kind of where you can memorize these specific bases. The small base, pretty much anything that's not a bulky base is safe to say it's a small base. Okay. So if you see this base, that means, first of all, if it's a base, you know it's going to be elimination. NaOH, for example, is a strong base, but you create the Zysov products, okay? Knowing if it's E1 or E2 isn't as important as knowing if it's Zysov or Hoffman, okay? It's not as important as like SN1, SN2, okay? Knowing E1, E2 just is simply strictly for like the special quality it has. If it's a weak base, then you can be like, maybe I can put it in a more favorable position by rearranging. And if it's an E2, you have to make sure you find a anticoplanar hydrogen to your leaving group. Okay. Besides that, where you actually place your double bond is dependent on the size of the base. If it's a small, it's going to be more substituted. If it's bulky, it's going to be less substituted side. Okay. Does that all make sense so far? Any questions? Okay. That's good to hear. I will give you guys one practice problem and see how you guys do. Okay, I will put it right here. So let's say there's a dash methyl here, a wedge bromine here, a wedge methyl here. Then I tell you to go where the base is NaOH. Okay, so go ahead and try to solve this if you have a notebook in front of you or wherever you're taking notes. I'll give you guys like about 2 minutes or a minute, and then I'll ask what you guys put. If you have an answer, go ahead and let me know. Just explain if we create a double bond here, so at the top or the bottom, right here or right here. Okay. Okay, so one of you guys put it at the bottom. Anybody else? Okay, so I got 2 for bottom. All right, so the bottom one is correct because these are methyl and I already predetermined if it's a wedge or a dash, that means it automatically becomes that the other side, or the hydrogen on those carbons, have to be opposite of those methyls. So if I have a dash methyl, I'm going to have a wedge hydrogen at the top. If I have a dash methyl, I'm going to have a wedge hydrogen at the top. And if I have a wedge methyl, I'm going to have a dash hydrogen at the bottom. Our leaving group is on a wedge. That means we want it to be anticoplanar to our leaving group because this is a strong base. The reason why it's a strong base is also the reason why it's a strong nucleophile, okay? Because of the sodium, this is an ionic bond. When sodium leaves, you have a complete separation of charge where there's a complete negative charge on OH, and that OH will use the negative charge to abstract this proton to create water. Okay, so that tells you it's E2, and E2, remember the rule is you have to find a anticoplanar hydrogen, and that's what we did with these purple lines. So it has to go right here. Okay, so your structure should look like this. Also, another thing is when you create a double bond, you no longer have stereochemistry on all of the carbons attached to that double bond. Okay, so that's why I kept this methyl group as a dash, because I don't have a double bond touching that dash. But this wedge methyl group, because it is now touching my double bonded carbon, it is automatically turned into a line because all of these carbons are now on the plane. Okay. So make sure you're changing the stereochemistry of substituents when they're bonded to a carbon that has a double bond. But keep this one. Don't change this one either. Or also. Okay. Any questions on this example? Okay. Any questions at all on what we did so far? Or anything you guys want to see? Any specific scenarios? Because other than that, I'm pretty much done. Yeah, no problem. Hopefully this will help you guys for your quiz on Thursday. If you guys are done talking about E1, E2, maybe we can get started on double bonds next week. Yeah, no problem. Thanks for coming. Have a great week and good luck on your quiz. Oh, sorry. Oh, God, it cleared. I did not mean to do that.